All right, guys. Let's just start with like a quick warm up. Find like a whiteboard space, and let's see if you guys can do this. This is a little tricky. I don't know if this is actually from your homework or not, but it's from your textbook. So this is a function graph. I want you guys to do a graph for just the derivative of this function. Okay. So again, that's the actual function, but you guys notice how the slopes are. Try to draw its derivative function. Okay. So if you don't know, try your best to draw this. Right. This is not easy. This is a pretty tough, tricky question. Oh, I'm so sorry. Yeah, go ahead and put the tub somewhere where everyone can access it, like on a table somewhere. Right? And then there's a sign-in sheet over there, so you guys can start signing in. Okay. All right. Good luck. I'll give you guys like 5 minutes to try to figure this out. What shape you guys get. And Sean, can you do me a favor and like close the door over there, so that way there's no light that comes in. Thanks, John. Is there a glare on this? Can you guys see? Or no, is there a glare where you guys are? Stevie and Emily? Can you not see or can you see? Okay, just making sure. If you can't see, I'll close the blinds. I'll show you guys the solution soon. So think of it this way, like where are the slopes still positive? So I noticed that the slope is positive from here to here, and then there's no longer any slope there. So from, I think, the interval of -4 to about -2, you should have something in the positive region, because that tells me the slopes are positive there. Okay. Remember, a derivative graph is how the slope at each point is doing. Okay. And then notice that the slope here to here, okay, isn't quite positive. You guys might be very surprised to see what the shape's going to look like. Maybe like 2 more minutes. Oh, you guys want me to turn off the heater? I think Alright, what'd you guys end up getting? It's alright, alright. Alright, I'm gonna show you guys what the answer is. You guys ready? You guys ready to see? I'll try to put like a little side-by-side comparison here. All right, so on the top is f, and the bottom is f prime. Who here got close to parabola? No? This is pretty tough, huh? Okay, let's explain why. So let's check it out here, okay? Again, let's see what the slope is doing. What would you consider this slope? To be a zero slope? It's a positive slope, right? All the way from the interval, again, from -4 to the top of x equals -2. This is all positive. So if you look over at the slope graph, or what I call the derivative graph, I would say roughly -4 or -3.5, all the way to -2. These are all positive values, right? But if you can kind of see the slope, right? They start off very straight, and then over time, as it gets closer and closer to here, we notice that the slope is flat. What is a slope that's flat? What numerical value is the slope when it's just a flat slope? 0. So if you can kind of see, the slopes are approaching 0, right? Here's a line, here's a slope, and here's a slope if I had to draw it. And eventually it hits a slope of 0. Here, it's the same case. The slopes are still positive, but up to about -2, where you see a flat slope, the slope is literally 0. Okay, so again, derivative graphs just tell you where the slope is at every single point. Right? How would you describe the slope from -2 to here? Would that be a positive slope, negative slope, or a 0 slope? You only really have 3 options. This is a negative slope because you can kind of see the line is literally just going down, right? However, if we keep going, okay, past the x-axis, is it still a negative slope? Yes or no? You guys see that? Is it still a negative slope? Yeah. All the way, yeah, that's absolutely right. From -2 all the way to -1, the slope is still, oh, I'm sorry, +1 over here. The slope is always negative. Up until this point here. Again, it dips, and there's a point where there's just no slope. There's nothing, okay? So wherever there's a flat spot, what I call flat spots, or minimum or maximum points, that's where your slope is 0. And that should tell you that that's where we switch slope. We switch the sign of the slope. These are negative slopes. If it goes to 0, and then it goes back up, that tells me all of these guys are positive. So let's take a look at what that's going to look like here. Okay? From -2 to +1, they're still all, these are all negative values, right? These are all negative values here. These are all negative y values. That shows you that from here to here, all the slopes are indeed negative values. But up to about up to +1 is where, again, it hits 0. The slope is 0, okay? And then from here to here, all the slope values are positive, okay? Very tricky concept, right? So you need to get really acquainted with this. This is not an easy concept, but these are very common questions that are going to show up on the AP Calc exam, right? And possibly this month's exam too. Okay, I might have one question where I expect you to be able to draw this sort of graph from the F graph here. Okay, it's a skill that you need to be able to see. You need to be able to see where the slopes are positive, where they're 0, and where they're negative. Okay, that's an essential skill. All right, any questions so far? All right, we're going to start notes. So everyone, please take out a piece of paper right now and get ready for some notes. We're going to cover 2 sections today. Okay. And they're going to be the last 2 sections. I think for sure we're going to get through the first section, but the second session, there is a lot I still want to cover. So maybe a video for that. Okay. So here it is, 3.3, the rules for differentiation. for differentiation. And then we're going to remind ourselves, let's see, that in the past, we've learned different techniques. Oh dear, okay. Let's see if I can fix that. Give me 1 second. I don't know what happened. This projector's giving me a lot of problems. To find. Alright. This is a pain. Okay, so go ahead and write this down. In the past, we've learned different techniques to find the instantaneous rate of change, which is otherwise known as the derivative of any function using limits. So we've been using limits of slopes, which is technically, we're just using secant lines. So what I mean is you have the limit as h approaches 0. We're doing f of x plus h minus f of x over h. We're finding the slope at 1 point, but the truth is we've been using a technique where we've been simulating that, where we take a gap between like 2 points, and then we make that gap go towards 0. It's a really good technique, but it's sort of inefficient. It takes a lot of time. And really, we're not actually taking the full derivative. We're just kind of simulating a derivative, simulating a slope. Like a slope at 1 point. We're really good at taking slopes at 2 points. Okay, we've been good since algebra, like slope, or which is rise over run, right? And then we just took an advanced version of rise over run. But now we're going to do something a little bit different. And hopefully it's something that you guys remember doing in last year's class at the end, towards the end, and maybe you didn't understand why. But hopefully by now you have some concept of why you've been taking derivatives, quote, quote. What are derivatives? Today we're going to review those things that you've done last year, and now you will finally step into the realm of doing derivatives much faster, okay? Without having to do the x plus h technique. You'll still need to go back to this once in a while, but from this point on, derivatives are going to be a lot easier, I think. Because there's just some derivatives you could take using this technique, but the limit of h approaches 0, but you probably don't want to. Okay, so here's the first rule. Write this down. This is the first rule you're going to learn. The derivative of a constant function. It says if f is a function with a constant value of c is a constant number, then if you take the derivative of that, you're going to get 0. An example would be if you have f of x is equal to 7, and you take the derivative. I'm going to give you guys a little time to write this down before I start explaining. Again, is there a glare where you guys are? No? Okay. Is there a glare where you guys are? You guys can't see. There is a glare? Okay. Oh, just making sure. Oh. Just had to make sure. And you don't have to write this weird thing where it says show graph for y equals 7 on Desmos. That's a note to myself. Which I'll probably do, actually, right now. Don't worry, the notes are still going to be up. Okay. The notes are still up. It's just I'm kind of moving this window over here while I prepare another window to show you. Right? So this is nothing new, right? I said that if f is a function with constant value of c, so c is like any constant number. If an f again, df means the derivative of the function, okay? If my function is simply equal to 7 and I take the derivative of 7, it's going to equal 0. Let's look at y is equal to 7. Is there a slope at all? Like, is there an increasing or decreasing slope at all for y is equal to 7? No. So that's why any constant value is just going to give me a straight line. There's no slope for it. Okay? So that sort of makes sense. Let's go to rule number 2. Oh, sorry. I'm kind of skipping ahead here. We'll do this one here, okay? Power rule for positive integer powers of x. This is where things get kind of nitty gritty, right? This is so much cleaner. It looks really complicated, but it's not. If you take the derivative of a function that has a base of x with some kind of power, don't overcomplicate it. Think of like x squared, x to the third power, x to the fourth power, okay? N represents some kind of exponent number. If you have to take a derivative of x to some power, all you need to do is drag down that number in the front and take 1 away from the exponent. And then that there is your derivative for that function. That's it. That's all you have to do. You don't have to do x plus h. You don't have to do all that stuff. You don't have to make h's disappear. All that goes away. This is a clean technique. So I have an example right there that I really wanted to show you. An example would be f of x equals x to the 7th power. You take the derivative of x to the 7th power. You take down this 7 to the front. You subtract 1 away from the 7. And you should get 7x to the 6th power. Okay? I'm going to give you the option now. I want you to do x squared on your paper right now. You can either do the limit as h approaches 0, or you can do this new technique and try to find out what it is. I'm going to do the old technique, okay? I'm going to do the old technique in the meantime. So don't worry about all that stuff. I'm going to do the limit as h approaches 0 of f of x plus h minus f of x over h. F of x is equal to x squared. Okay, and then I'm going to have the limit as h approaches 0 of x plus h squared minus x squared over h. So I'm doing the old way. You guys do the new way. I have a x plus h times x plus h minus x squared over h. I think I'm going to beat you guys. I have a good feeling I'm going to get this before you guys, right? Am I wrong? Let's see. No, you're not. You silly goose, you. How could you be finished before me? This is the much faster technique. The limit of h approaches 0. Okay. You guys are still going, aren't you? So sad. You can't beat the teacher, right? Okay. Then you have this. You have 2x plus h. The limit as h approaches 0. Okay, and I plug in 0, so that'll give me 2x. You guys finished yet? Have you guys been finished this whole time? Okay. Did you guys get 2x with the new technique? Okay. All right. So dang it, I was wrong. Which technique do you guys prefer? The limit of h approaches 0 or this new technique? This new technique. Okay. How about we do some new ones on, I would dare you, I'm only going to dare you to do the limit of h approaches 0, okay? If you can get one of these equations under h approaches 0, I will give you extra credit. But here's what you're going to do on the whiteboard with a partner, okay? Just work with someone. And I want you to do A, B, C, D, E, the new technique, okay? Let me make that clear. But if you want to do it the old way and you get the right answer, then I will give you a little bit extra credit. So please do these 5 questions first, okay? The new school way. And then if you have time, go back and see if you can try the old school way. Good luck. Best of luck. C and D are a little bit weird with the 2 and the 4 present there, but I mean, what are you going to do with the 2 and the 4 there? If you don't know, I'm going to walk around and help, so I'll answer any questions you guys have. And then if you subtract 1 away from -2, technically it's not, it's negative, it's a bigger negative. There you go. It's weird, huh? You gotta kind of think like that. Yeah, so like on C, if 2 was there, when you bring down the 3, yeah, that's correct. Very good. Oh my, you're really doing it. That's a dang. If you have time, you can dare to walk on the wild side and try the limit of h approaches 0 if you like that. I thought more of you guys were going to the PSAT. I thought you were going to the PSAT, but yeah. But then they told me you're seniors. So yeah. Oh, okay. Alright. Let me go around and help. Any questions so far? For you guys? What are you doing here? Very good. Very good. Okay, and then yep. Yeah, I'm so oh, okay. Do you have any questions? Cool. Yes. Great. Very good. I'll just start doing solutions right now. Alright, I'll give you guys another minute. This is really tough stuff here. What are we doing next? Alright, now we're going to stop. Did anybody get one for the limit of h approaches 0? Did you guys finish one? Or close? Or no? Was it? No? I'm glad you started. Yeah. Okay, well, that wasn't to discourage you or anything, or it was just to try to prove a point. Some of you guys that are doing the h approaches 0, like I heard, I heard Gabby. She was saying for C. Whoops. Sorry about that. So when Gabby was taking the limit of h approaches 0, she had to bust out Pascal's triangle. Okay, I'm just trying to prove a point here that this might be the way to go in the future now if you're going to do derivatives, especially because I've only given you. Usually, my only problems that I gave you were like x squared, 2x squared, functions like that. With this technique, I can give you problems that are like going up to the exponents of 8, 20, in theory, 100. You still wouldn't be scared anymore, okay? Otherwise, yeah, we would have to bust out this thing called Pascal's triangle where you have to look at what the I'm not going to get into it. It gets really complicated, okay? This next rule, you can write down. You don't have to. You've already actually done it without even knowing it. So maybe just read it for a second before you write it. Because rule 4 you'll need to write. Rule 3 you might not need to write. It's called the constant multiple rule. Basically, if u was the equation, u is differentiable. That means if u was like an equation, u is equal to 2x plus 7 or something, right? And c was a constant. What you do is you take out c, and then you take the derivative of u, and then so forth. Let me show you, like what you just did, 2x to the third power. Let's say that this guy is u, quote unquote. X to the third power is u. The constant is c. Our constant is 2, right? All you did was, this is just overcomplicating things. You knew that when you took the derivative of x to the third power, which is 3x squared, you just multiply that constant in the front, right? That was it. I think everyone here did that. On your C, on your actual C, everyone already did that. On D, you already did that too. So really, if you don't want to overcomplicate things and confuse yourself, maybe it's beneficial for you not to write these notes, okay? That's a pro tip too in college. If you can't write down everything the professor is saying, right? Shorten it down and then write down only the things that you don't understand, or just write down the things like, I do know that, but I probably won't remember it for the exam they're going to test me on, okay? So your notes should just be sort of things that are kind of new to you and not too redundant. So when you're writing, I always used to look at the students around me. There's always a student that was like, kind of looked up, was like, I don't need to write this, you know? And then there are the other students that thought, I don't know, the other students, I thought for a while, I'm like, I'm just going to take it all in, right? I don't need paper, okay? And then during the exam, I had no idea what to study for, okay? So don't do that either, right? Unless you're just that type of person. But I thought I was not. I knew what type of learner I was. Okay, anyways, I digress. Let's write this one here, okay? The sum and the difference rule. I'll give you guys like a few seconds to write this down, and then I'll discuss what the heck you just wrote down, okay? As you're writing it down, try to figure out what's going on, because it's not that complicated. It looks so complicated. I think higher levels of math look really complicated when you write down the notes and you study from the book. But then when you actually do it, it's so much easier than it looks. Huh? Yeah, you just get rid of it, because you know that derivative of constants will just be 0. Constants give me a 0 slope. Okay. If you didn't follow what Stephanie brought up, it's okay. It was just like a side note, and then we're going to bring it up again. Right. See if I can grab a little laser. Oh, this one here? It's a very confused one. Okay, there it is. Okay. He doesn't know exactly what it is, but it's a 1. Or is it 1? No, it's a 1. It's a 1. It's not a 7, it's a 1. See, 33. Let's get this at that time. Alright, I'll give you guys a few seconds. Alright, so I guess I should do this on the video here. Okay, actually, let me see if I can point this. Maybe it's a little easier. Okay. So this looks really complicated. It says if you take the derivative, okay, again, the derivative of whoever's in here with respect to the fact that it has an x, okay? The x is the variable, okay? Like in your equations over here, okay, your x was the variable, the input variable, the thing that you're plugging in numbers, okay? So that's what this dx means. I have to remind you over and over again, okay? The notation's not easy to understand. The derivative with respect to x of u plus or minus v is equal to the derivative u with respect to x plus the derivative v with respect to x. So easy. I'm just kidding. It's not. I think it's really complicated. Okay. What does it mean? Right? It looks really complicated, but it's not. I don't think it's too bad. Okay. Kind of, yeah. I mean, if you look at it here, x to the third minus 2x squared plus x plus 1. Each of those components can be its own function, right? Its own equation where you can take its derivative each time, right? What does that look like? All you need to do is literally look at each component and take the derivative of each guy. Okay? Out loud, if you could just share with me, I'm not looking for hands here. What is the derivative of x to the third power? You take the 3 down, and it'd be 3x squared, okay? How about the derivative of minus 2x squared? Anybody have that one? That'd be minus 4x. How about the derivative of x? Anybody get it? It is just 1. Why is that though? Because if you
Because x is really just x to the first power.
Yeah, or look at it this way. If I draw, like, look at my imaginary, imagine I'm on imaginary graph paper here, and I have a straight slope that goes like this, right? Straight slope, and it's x, okay? This is a slope of 1x, okay? Remember mx plus b? M would be your slope. Since there's nothing in front of this x, your m is 1. That means the slope here of my arm is literally 1. So when you take the derivative of x, you're literally just taking the derivative of 1. Does that make sense? Side note, does anybody know what the derivative of 2x would be then? If you want to do the power rule, let's take a look at what you would do. The 1 would get carried down, right? So that's 2 times 1, right? And then x would be to the power of what?
0.
Because you're subtracting 1 away from there, it's to the power of 0. Anything to the power of 0 is technically just 1. Okay? It's a little confusing. It's 2 times 1 times 1. That's a 1, I know. Okay? I write very confused numbers, but it doesn't do that. That's just a side note, okay? You don't have to write that. And then the derivative of 1 right here is 0. So all you have left is negative, wait, did I do it right? Sorry, that's a, yeah, it would be 3x squared minus 4x plus 1, and that 1 goes away, okay? Over here, anything that's constant is a value of 0, and then here would be negative 2x to the negative third? Or no, I'm sorry, negative 2x. That would just be negative 2x. So there you go, negative 2. Okay. Let's try another problem. 120 in the book. Okay, this is written a little differently because it's using a different variable, but the notation is correct. Take the derivative of p with respect to the variable that is now t, meaning if your equation is p, not y anymore, p is equal to t to the third power plus 6t squared minus 5 over 3t plus 16. What is your derivative going to be? You do not have to do this on the whiteboard. You can do this on your paper, okay? But I would highly suggest talking to neighbors right now on how to do this. All right, so take a minute to just figure that out. I'll show the solution in a second. Then we're going to go over two brand spanking new rules that are going to be a little tough, right? They're a little weird. They're a little odd. Now I'm going to give you another one. So let's double check to see how we did. Once I unpause the screen. Is everybody finished? Okay. So here's how they did it. Your final answer is at the bottom. It's 3t squared plus 12t minus 5 over 3. And if you're wondering about the notation here, they literally just took each component and they took the derivative of, let's say, t to the third power with respect to t. Okay? Here, they took the derivative of 6t squared with respect to t. They took the derivative of 5 over 3t with respect to t. They took the derivative of 16 with respect to t. Okay? That's what that means, right? D is just this d over here. It's just derivative. And then on the bottom, it tells you what the actual variable within the equation is. It's t, okay? Any questions so far? Try these two on for size. I would suggest not doing this on your note paper and doing this on like a scratch piece of paper. Or if you need more room, try it on your whiteboard. If you have any problems with this, that's perfectly normal. I'm just trying to prove a point here that these are not easy to figure out. I want you to take the derivative, so the derivative of this guy with respect to x, the derivative of this guy with respect to x. Sorry, that's what I'm asking you to do. Okay. Is anyone close to finishing the first one?
Oh, fine.
Yeah.
I mean, the assumption that I don't know true.
Sean, did you have something?
I got 5x power 4 plus 3x squared plus
3x squared plus 2x. Okay, so let's see if that's, let me see in my notes if that's correct. Whoops, sorry. So let me back that up for a second. Okay, so that's, oh, why does it keep doing that? Oh, yeah, it's good. So I do an arrow, and then I gave Sean's solution. See if you got that right. It is actually correct. It's just there's a certain way I want to do it to show you guys. The bottom one, though, I think is where things get really tough. The top, there is a way you can kind of finagle it, but the bottom is pretty tough. Anybody want to spend more time? Does anybody want me to go over it now?
I totally didn't see the first one, though I haven't been working yet.
Oh, okay. I'll give you guys about another minute, and then we'll discuss in class 2 new rules. Coincidentally, there are 2 problems on the board, so maybe I should tell you that these rules will help to explain how to solve these a little bit easier. Okay, 30 more seconds. You can try this out. Okay. All right, anybody get an answer from the bottom one so
I
far?
got 2/3, which was like just taken by doing the derivative of the top and then the derivative of the bottom, and then so like the first one, so the top was 2.
Okay, so you got 2/3. Sean, what did you get?
19 over 9x squared minus 12x plus 4.
9x squared and what?
Minus 12x plus 4.
Okay, very good. Anybody else? Okay, I'm glad most of you are like, huh? Okay. Because I would very much be in the same position of, huh? What's going on here? Okay, let's go through this together. I'm going to write it down. I have it written down, but I want to write this down with you guys. Rule number 5. It's what we call the product rule. If you take the derivative with respect to x of what we call u times v. Remember the last statement was u plus or minus v. This is if we have 2 things that are being multiplied to each other, like they're attached to each other. U times v, what you're going to end up doing is u times dv over dx. You're going to leave u alone once, and you're going to multiply it to the derivative of dv over dx. Then, you're going to do the opposite. You're going to add that to v times du over dx. Let's look at our example from earlier of x squared plus 1 times x cubed plus 1. And I asked you to take the derivative with respect to x. I wanted you to get the derivative of x squared plus 1 times x to the third power plus 1. Let's use the new rule. What would I assign as u? And what would I assign as v? If I had to make this comparable to this technique, what would my u be and what would my v be? Yeah, so let's just make, because these are 2 things being multiplied to each other, and could you take the derivative of u alone? If it was just u, x squared plus 1, could you take that derivative? Yeah, that's not too bad. You take that derivative. It's only when you multiply these two things that make things really confusing. So you have to take this rule. If you don't like it, because there's a way to prove that this is actually correct, from last year I posted up a video on why this rule just comes out to be. There are these things called proofs where people just go through like how the old Greek philosophers, if you can imagine these people in like their robes, just flaunting about, figuring out math and finding out things in nature. Okay, they just sat there on the wall and then just wrote things out until suddenly they found a formula that works consistently in nature to explain most of these things. Well, they found a way to prove that this actually works. This isn't arbitrary, okay? This isn't necessarily quote unquote man-made. It's something that we transcribed from patterns in nature, and they just found out that this works. Anyways, I went a little bit too far in explaining that, okay? Sometimes Mr. Wee does that. But if you want to find how this is proven, I have videos online on my website. You don't need to know where this comes from, but if you don't like memorizing these things, there's an awesome video by like an older gentleman. I forgot his name. He's an old professor. He actually takes a few minutes to actually work this out and show you that it works all the time. This is a really cool. That was a really cool video. But you don't feel pressured to do it. You already have a lot on your plate, okay, as students. Okay. So, anyways, let's do the first step. It's u times dv over dx. If it was just u, it'd be x squared plus 1 times dv over dx. Okay, dv over dx. That just means the derivative of x cubed plus 1. What is the derivative of x cubed? Can you do that in your head? 3x squared. And what about 1? Nothing. That's it. That's u times dv over dx. I'm not quite finished yet. I gotta do v times du over dx. V is left alone now. Now we take the derivative of u. Can someone tell me the derivative of u? What is the derivative of x squared plus 1? That would be... What is the derivative of x squared? 2x. What's the derivative of 1? 0. So 2x. Let's, at this point now, oh, careful there. At this point now, oh, don't forget to sign in, guys. That's the sign-in sheet, by the way. Thank you very much. I know it looks weird, but it's just, this is the distributive property written in a little bit of an out-of-order fashion from what you're used to seeing. It's just this, what I'm trying to say is you just take both of these numbers in this parentheses and you multiply it by the outside number, which should be 3x to the 4th power. I know, it's kind of weird. How do you deal with exponents being multiplied together? Okay, might want to review that. And then over here would be 2x to the 4th power plus 2x. 2x. You combine like terms, you get 5x to the 4th, because there's 3x to the 4th and there's 2x to the 4th. So you can combine those to make 5x to the 4th plus 3x squared plus 2x. Now, I'm curious. Okay, I meant to circle the 2x, okay? I didn't mean to just separate that person like that, okay? I'm curious. Someone gave me a potential answer. Let's see if that person got it right. That's not it. So, who gave me this answer? Was that you, Stephanie? Sean. Not bad, Sean. You were able to do it without the product rule. Like, well, kind of, yeah.
You were, like, you just multiplied it in advance.
Yeah.
And did the derivative of that.
With the sum and the differences rule, right? Like, yeah. This right now, in this state, you actually didn't really need to do the product rule to solve this. You could have just multiplied this out and then taken the derivative. But you will have instances where you definitely need to use the product rule, and you have no choice but to use it, unless you want to go a much harder, much longer way, okay? I'm going to give you rule number 6 now. It's so important that gotta do it in a different colored pen. That's how crazy we're getting here. Okay. That's how wild and crazy we're getting here. So this is if you have this type of problem, you're given the derivative of u over v. Ooh, if you have two statements that could be, what is it, derivatized? That's not the word. Differentiated. If you have two statements that are different, you could differentiate, and they're written in sort of a fraction form, okay, or what we call quotient, then this is what you're going to have to do. Oh, you're going to love this rule. It's just going to be fun. It's v times du over dx minus u times dv over dx all over v squared. Doesn't that just roll off the tongue? You guys are going to be able to memorize this in a day, right? Okay, maybe you're not. But I got a cool saying. Back in my time, this is what we used to say, okay? I call this low D high, comma, high D low, square the bottom, and away we go. It's an all famous saying by me. Okay. I didn't make it up, but someone else did for sure. Okay. So that's what we used to say in the old time. Low D high D low, square the bottom, and away we go. What the heck does that mean? Right. All right. Well, actually, can you figure out what that means and what that has to do with this at all? What the heck just?
So square the bottom in the bottom.
Okay, all right. That makes sense. There's a square on the bottom. Okay, so I squared it. That makes sense. But what the heck is low D high D low? Any thoughts on what that could be? I'll explain it in just a second.
The one on the bottom.
Wait. First off, what is the one on the bottom? What are you talking?
Denominator.
Oh, here, the v. Yeah. Okay. So it's low.
The derivative of
the high guy. Okay.
And then high.
Which is the u.
The derivative of
the low. Okay, so let's look at that again, okay? I know this is weird, and the order does matter. Before, I will say this. You could have taken this out of order. You could have taken v times du plus u times dvx. The order does matter here. It's very specific because the subtraction sign makes everything weird. Meaning you have to put in this order. Here's what I mean. Let's consider this guy, the u, to be the high part of the fraction, okay? High. The v is the low, right? So the first step is low d high. Low, you take the v, which is on the bottom, the low guy, and you multiply them times the derivative of the high function u. Does that make sense? Low times d high. Does that make sense? Yeah? Low times d high. And you subtract it by now the high, which is u, okay? U times the derivative of the lower function v. dv over dx. dv over dx. And then, of course, you take this part doesn't really explain it, but you do have to take the v with whoever's on the bottom and you square him. And away you go. You're finished. You can walk away from the exam feeling a little bit more proud of yourself. And even if you didn't do that well, it's okay. You can still walk away proud that you tried your best because this is a hard class, okay? All right, let's give you an example here, okay? Let's take the derivative of 2x plus 5 over 3x minus 2, okay? Can you at least identify for me the u and the v? What would the u be and what would the v be? Do we have a top portion that you can take the derivative of? Yes? I think you can. That's 2x plus 5. So that'd be v, or u. The bottom would be 3x minus 2. I could take the derivative of each of these guys by themselves, but combined, they make a much harder problem. So let's try this out. Low d high. Let's take the low. It's 3x squared, or 3x minus 2. Leave him alone. And then I'm going to take the derivative of 2x plus 5. What is the derivative of 2x and 5? Just 2. That's it. Then high d low. That means you take the high, 2x plus 5, which is just... I'm sorry. High you keep by itself. 2x plus 5 times d low, the derivative of 3x minus 2. What would that be? Yeah, it'd just be 3. Square the bottom, which is 3x minus 2. And away we go. That's it. I can't go any, I can't do any better than that. So that's as crazy as it gets. Now I'm gonna just do the math here. I'm gonna distribute the 2 into here. So it's gonna be 6x minus 4 minus 6x minus 15. You can check the math there to see if there's anything incorrect. Okay. I'm not gonna do anything fancy with the bottom. I'm just gonna leave it as it is. 3x minus 2 squared. But I do notice when I combine like terms, the 6x and the 6x here, the minus 6x here, will cancel out. So I'll be left with negative 19 over 3x minus 2 squared. And ladies and gentlemen, that is it. You've successfully completed the low d high d low, square the bottom, and away we go. Sean, your answer was actually correct. Again. How could you, Sean? I have, the bar is here, and you are right here. No, I'm just kidding, Sean. Yeah, you did good. I have no idea how you did that on your own, so. Because by this time, I would be like, I still don't understand this, okay? Let alone all this stuff, okay? I'd be just stuck right here, okay? Okay, enough talking. Are you guys in here for the doing? Yes? In my time, that means sample problems. You see? Okay. So let me get you your first sample problem. Where's the problem here? Wait, this better not be the same problem. Oh, shoot. Hold on, give me a second. Example number 4. Oh dear, that's the same problem. Okay. 1 second. Did I not pick a good one here? X minus 2. Here we are. Okay, here we are. Example number 5. Don't worry about support graphically. You do not need to do that port. Okay. Good luck. Whiteboard space time. Go. Capiche. Which rule do we use, good sirs? I do not know. So if you can't remember it, just remember the old saying, low d high d low, square the bottom, and away we go. I have a good feeling we're not even going to touch 3.4. Did you guys want to do a lecture on Friday, or would you rather me make a video, a series of videos? Raise your hand if you would like a class lecture, like where you come on Friday in your own time and record. Raise your hand if you like me to make videos. Oh, okay, right. I guess videos wins. Okay, all right, just making sure. Last year I offered in, some people wanted to do Friday. Okay, all right. Continue, good people. Be warned though, there's gonna be a lot of videos. So it's gonna be, oh god, it's gonna be like 3 hours. No, it's not gonna be that long. Probably about an hour's worth of stuff to watch. So be on the lookout. Wow, I love your math. You guys just go good. Yeah, I like it. Very clean work. Very clean work. Very clean work, guys.
Oh my gosh. You follow me? Figured out.
E?
What? It's like the old fashioned way. Okay.
Oh, did you? Oh, from
From way before, yeah. Okay.
All right. Did you? Yeah. Let me see.
All of them. You was like. Well, A might have been the worst, but yeah, we did it. So, but then everything comes along, so it's okay. Yeah.
Oh man, so you seriously did it. You did all of them.
Yeah, we did.
All right. Let me give you some extra credits. Wow. In the back, they were attempting.
Did you write on this?
Plotting their
This
attack.
This is irrelevant now. Because I was like, I looked at it, and I looked at it, it's like, okay, I see what you did.
Okay, so Ashlyn, and Teresa, and Gabi. I'll say, for some reason, Mr. Spiegelberg likes to call you Gabi.
Yeah, I don't know. Everybody knows that.
Yeah, I was pretty intimidated by you when I first met you. I was like, she.
Gabi?
Yeah, she's like, hello, Miss Gabi. Okay, all right, there we go. Here we are. Okay. All right. Okay. Let's check it out, Tio. Anybody get 4x squared over x squared plus 1 squared? So let's take a look here. U is x squared minus 1. V is x squared plus 1. So the first one is, what is this? Lodi high. Okay. Lodi high, which, okay, you didn't see this, did you, kids? Okay. Let me just make it. I think it's just unfair the way they write this, right? So it's x squared minus 1 over x squared plus 1. Okay. Low is x squared plus 1 times d high. D of the high, the derivative of the high is this guy, which is just 2x, minus. That's the big key. You have to subtract. Okay, you have to subtract. Subtract high, x squared minus 1, d low, the derivative of the bottom, which is 2x. Doesn't that look familiar? Okay. Square the bottom, and away we go. Okay, so let's just take the bottom and square it. And then you should be left with 2x cubed plus 2x minus 2x cubed plus 2x. Hey, what the heck? All that hard work for nothing? No, I'm just kidding. So those are gone. The 2x's combined, and you get 4x. And then this on the bottom remains the same. I like the bottom because it never really does anything else except square it. So that's it. Okay? Any questions? Okay. Don't worry about Ender. Okay? I only showed you that one time in one of the videos. I don't think I'm ever going to make you do it again. Okay? But if you had to check the derivative, I think that's one way you could check the derivative. You put in a function. Actually, if you mastered this little technique, that could save you a lot of time too. But just be aware of that on your exam, when the AP exam, you won't always have the calculator next to you. Okay, well, I got we're still on 3-3. I know. Okay, you guys are like, oh, don't like this. Okay. What's the date today, by the way? This is month 2, week 3, the 10th. 10, 10, 18. Just gotta make sure I get these extra credit points. Alright, shitums. Okay, no more rules. We're not gonna break them though. I'm not envying that, but no more new rules. Okay. We're gonna be finding the horizontal tangents. This is a type of problem. Horizontal tangents. What the heck does that mean? Something tangent.
That's horizontal.
That's horizontal, okay. At which points of your function, okay, again, a fancy way of saying equation of your function, will you and only you, I'm just kidding, will you have horizontal tangent slopes? We must dissect what all of this means. I'm so sorry. At which points of your function, okay, that is your equation, right, that you're graphing, will you have a horizontal tangent slope? First off, another way of saying tangent slope is what you've been doing this whole time. Derivative. Derivative means you take the slope at one point. Tangent means you take it at one point. Secant means you take the slope at 2 points, okay? But the whole crux and the whole beauty of calculus is learning how to do it with one singular point. The tangent, okay? Get it? The tangent. Not the secant, the tangent. You're taking the slope over here, and guess what? That's another way of saying derivative. When I say horizontal, though, when I say horizontal, that is not a horizontal slope. What kind of slope would that give me? You have 3 choices: positive, negative, or... It's a positive slope, right?
Horizontal is just a straight line, like the not like tilted at any way.
Well, Stephanie, I was getting to that, Stephanie. Okay, I didn't want to blow the surprise. Okay.
Slope is 0.
Yeah.
So
Stephanie. Stephanie.
But I know this.
I was gonna blow everyone's mind. Or not. Okay, it might have just been redundant. Okay. Going down means that you have a negative slope. It's still a number. -5, -10. This has a slope of -600, right? But don't draw this. You're going to have weird lines on your paper, okay? So don't do that. But if you have a horizontal slope, what is the value of that slope? 0. So horizontal means the df over dx, your derivative at that point is going to be equal to 0. So let me give you... So there. That's what this means. Horizontal means the derivative is equal to 0, and you have a tangent slope. That means the derivative. Where is the derivative equal to 0? That's what I'm asking. Your example would be this. Y is going to be equal to 5x cubed minus 3x to the 5th power, right? Where is the derivative of this guy equal to 0? First off, why don't we just take the derivative of this guy really quick? We don't have that much time, so please do this quickly on your paper. I will do this on my paper as well. I will get 3 times 5 times x to 3 minus 1. I know it's weird the way you're seeing it, but I have to make sure you have it written the full way. It's 3 times 5 times x 5 minus 1. You don't have to write it my way. You can just do the derivative. But what I got was 15x to the second power minus 15x to the fourth power. Is that correct? Did you guys get that? Okay. I'm going to do a weird thing, and I'm going to factor out that both of these guys have 15x squared in these guys. So it's going to be 15x squared times 1 minus x squared. Okay. I'm going to rewrite this in a weird way. It's 15x squared. You're going to see why. I'm going to have this minus x squared plus 1. I'm going to factor out. A negative 1 from both of these numbers. So I'm going to factor out. So I'm going to say I factored out negative 1 from this step. And then it's going to be negative 15x squared is going to be x squared minus 1. Again, if you don't understand what I did, go home and review what you just wrote down, okay? And I'm asking you, at what points is my derivative equal to 0? So this becomes a very algebraic problem. If you don't remember how to do that, I have x squared minus 1. You might not remember the name of this. This is called a difference of squares. When you expand this out into two binomials, or two parentheses things, okay, it's going to look like this. X plus 1 times x minus 1. Again, the x squared and minus 1, those are squares. You can take the square roots of both, and they're being subtracted. So that means you have two binomials which look a lot alike, only separated by different signs. You have to solve the values that give me 0. What values give me 0? Well, if you set this equal to 0, negative 15x squared is equal to 0, you can do a little bit of math. You don't have to write any of this down. Some of you guys won't need to. It's x squared is equal to 0. I take the square root of both sides. Guess what? One of the answers is x equals 0. One of them is x plus 1 is equal to 0. You subtract 1 from both sides, get x equals negative 1. Do you guys remember doing stuff like this where you had to take the roots? And then x minus 1 is equal to 0. You add 1 to both sides. At those 3 points, this graph should look flat. Their slopes at these 3 points should have a slope of 0. Is anybody still writing this? I just wanted to show you this really quick. Be packing up simultaneously, though, because I know we're going over a little time. I'm sorry, okay? Just want to make a point, that's all. I just want to make a point, guys. Okay, sorry. 3x to the 5th power. Okay. Wait, guys, wait. Okay, as you're packing up, if you can, look here at negative 1. Look at that slope there. It is flat. That is a slope of 0. At 0, that slope is flat. There is no slope there. Well, I mean, there is, but it's just 0. And then at one more point over here, at positive 1, the slope is equal to 0, or the slope is 0. I hope you understand that now, that at these 3 points, you have figured out where the derivative is equal to 0 and where they have a horizontal tangent slope. Okay, you guys are good? Stack away your chairs. Go home, kids, or go to your next class. I'm sorry, okay? Have a good day, okay? Have a grand old day, kids. Have a grand day.